Hello, AP Chemistry students. We're now on Unit 7, Part 2, and this one's on the influence on equilibria. And this covers sections 7.9 through 7.13. Our learning objectives here are to identify the response of a system at equilibrium to an external stress using Le Chatelier's principle, to explain the relationships between Q, K, and the direction in which a reversible reaction will proceed to reach equilibrium, to calculate the solubility of a salt based on the value of Ksp for the salt, to identify the solubility of a salt and or the value of Ksp for the salt based on the concentration of a common ion already present in solution, and then to identify the qualitative effect of changes in pH on the solubility of a salt. So we've talked a bit already about equilibrium and how the concentrations of reactants and products can affect the balance between them, causing them to shift towards the products in the forward direction or shift towards the reactants in the reverse direction, and how this can be controlled by the equilibrium constant. Now, today we're going to talk about how the balance between the reactants and products can be upset by adding stress. And what we mean by that is taking a system that is already at equilibrium and then changing it somehow. And these stresses, these changes, can come in the following forms. A change in concentration, so either we're changing the concentrations of the reactants or products, changing the temperature of the system, or in some cases, changing the pressure of the system. Now, what I'd like you to do right now is pause this video and check out the video that I've linked here. I've also linked it in the description of this video. And I want you to watch this experiment on a concept called Le Chatelier's principle. This is a really, really important concept in equilibrium. So now that you've watched that video, let's talk about that experiment. So cobalt chloride as a solid, when dissolved in water, will generally form a purple colored solution. And that's because there is an equilibrium between cobalt hydrate, a cobalt ion surrounded by water molecules, which makes the solution pink, and then cobalt chloride, which is a cobalt ion surrounded by chloride anions. And it's usually somewhere in between. You have a mix of the hydrate and the chloride because the water molecules and the chloride ions are sort of wrestling for the attention of cobalt, and it's usually pretty balanced in the middle. However, there are a couple things that we can do to this equilibrium to upset it and cause it to shift more in one direction. And you saw in the video that the different things that were done were to add hydrochloric acid, aka adding more chloride ions to the solution, adding water, which will add more water molecules, of course, and then heating and cooling the system, either by putting it on a hot plate or putting it in an ice bath. And from the video, we saw the following effects. When we added HCl, it turned the solution blue. When we added water, it turned the solution pink. When we heated it, it turned it blue. And when we cooled it, it turned it pink. And let's think about why all of these things are happening. So how did increasing the concentration of the reactants affect the equilibrium? Well, when we were changing the concentration of the reactants, we were changing it by adding hydrochloric acid, aka Cl- chloride ions. And it shifted it towards the blue, which meant that adding reactants pushed it towards the product side. And how did increasing the concentration of the products affect the equilibrium? Well, that's the reverse. When we added more water, we were technically adding products, and then that shifted it back towards the pink. And the reasoning for this is based off of something that we've already talked about. It has to do with the reaction quotient Q and its relationship to K. So we learned before that Q wants to equal K to make the system reach equilibrium. And if you recall, Q is calculated the same way as K, being a ratio of the concentrations of the products over the reactants, all raised to the power of their coefficients. And we learned that if Q is too big, it's going to want to decrease the amount of products to shift it back towards the reactants to make the value of Q equal to K And then the vice versa situation, if the Q is too small, it's going to shift it to make more products in order to increase the numerator of the ratio in order to make Q and K equal again. So this makes sense when we consider this experiment, because when we increase the concentration of reactants, our Q was too small because our denominator would have been too big. The concentration of our reactants would have been too big, and therefore it shifted towards the products to alleviate that unbalance of the reactants and products. And then the same thing happens when we increase the concentration of products. We have too much over here, and our numerator is too big, so it's going to shift back towards the reactants to alleviate that, and then make Q equal to K again. So now let's talk about how changing the temperature of the system affects the reactants and products and their balance in the equilibrium. And we're also going to talk about whether heat is a reactant or a product in this case, and whether that means the reaction is endo or exothermic. So you can't really figure this out without either knowing the enthalpy of the reaction, and I'll talk a little bit about that later, or if you can do the experiment and literally see how the equilibrium is shifting based off of the addition or removal of heat. So if you remember from the experiment, when we added heat, it shifted it towards the products. And when we removed heat, aka cooled it, it shifted it back towards the reactants. So I asked the question, is heat a reactant or a product? Well, what does that mean? If you think about reactions, some of them require heat to make products, and some of them release heat as a result of making products. And we call those endothermic and exothermic reactions, respectively. And in this case, we can add heat to the equation to indicate which side of the equation heat is needed to then push to the other side. In this reaction, we saw that the addition of heat pushed it towards the products, which means that heat is kind of like a reactant. And in this case, that means that the forward reaction is endothermic, because when we added heat, it shifted it towards the products. And if we were to remove heat, when we cooled it, it shifts it back towards the reactants. This means that our forward reaction is endothermic and our reverse reaction is exothermic. And that makes sense because if I'm going in the forward direction, I'm adding heat and then I'm making products. And in the reverse reaction, I'm going towards the reactant side, and heat is one of the reactants that will be produced as a result. The adding heat or removing heat works through the same mechanisms as adding concentration or removing concentration. It acts as a stress on the system in which the equilibrium will shift to sort of alleviate that stress. It's always going to try to undo what you did to it. Now, what would happen to the equilibrium if we added silver nitrate? Now, this wasn't covered in the experiment, but I want to talk about it. So when silver nitrate is added into the solution, the silver is going to react with the chloride to make silver chloride precipitate and then nitrate ions. So even though this is like a separate reaction, it's going to affect the equilibrium because the silver is going to combine with chloride and make silver chloride, and that's removing chloride from the solution. So if I'm losing chloride on the reactant side, that's going to upset the equilibrium. And since it wants to alleviate any changes that we made to the system, some of the cobalt chloride is going to shift back towards the reactants to make more cobalt hydrate to then balance out the amount of chloride in solution. So removing reactants also causes the equilibrium to shift, and it's going to shift towards the side that will make more of the thing that you removed. And just one note, this is going to affect the overall reversibility of the reaction, since silver chloride is highly insoluble, and once those chloride ions are removed, they can't really come back. All right, now let's consider a gaseous equilibrium, and let's consider the same mechanisms for Le Chatelier's principle that we discussed in the last example. So say we have a hydrogen gas and oxygen gas, and they are in equilibrium with water vapor gas. And we know that the delta H, the enthalpy of the reaction, is negative 480 3.6. This should be in kilojoules per mole. Whoops. Now I want to know what would happen if hydrogen gas was added, what would happen if hydrogen gas was removed, what would happen if water vapor was removed, what would happen if the reaction chamber was heated, what would happen if the reaction chamber was cooled, and then we're also going to speculate what would happen if the pressure of the chamber was increased. Let's go over each of these concepts individually. Let me add the units here. All right, so what would happen if hydrogen gas was added? Well, like we saw in the other examples, when we add something to the reactant side, it's going to want to push it to the product side in order to balance things out and make Q equal to K again. So by adding hydrogen gas, it's going to shift it towards the products. Now, what would happen if hydrogen gas was removed? Well, much like the silver nitrate example, by removing something, it's going to shift in a way that will make more of the thing that you removed. So if I remove hydrogen gas, the water vapor is going to want to shift back to the reactant side to make more hydrogen. So that's going to shift it to the reactants. And by the same logic, if we were to remove water vapor, that would shift it towards the products to replace the water vapor that was removed. Now, what would happen if the reaction was heated or cooled? So I mentioned earlier that you would either need to do an experiment or know the enthalpy of the reaction. So we know that this reaction is exothermic because it has a negative enthalpy value. And in the last example where it was endothermic, we treated heat like it was a reactant because we needed heat to progress towards the products. Whereas in an exothermic reaction, heat is kind of like a product because heat is being produced as a result of the reaction. So I added a little E here to represent the energy being released because it is an exothermic reaction. So we can treat the energy or the heat as if it was a product. And if we apply the same mechanisms, if we were to heat it, that means we already have energy here on the product side. So if I'm adding more energy to it, it's going to want to shift back towards the reactants to alleviate that. It's going to want to cool it down as a result. So it's going to want to shift in the endothermic direction. Whereas if I wanted to cool the system, we'd end up pushing it more towards the product side because that's kind of like removing energy from the system. And it's going to want to shift in a way that will produce more energy to alleviate that change. So now let's talk about what would happen if the pressure was changed. And more specifically, what would happen if the pressure of the chamber was increased? Well, if you think about what pressure is collisions. So increased pressure in the system will mean more collisions between molecules. And since equilibrium is always trying to undo any sort of change that you do to it, by changing the pressure, you're making more collisions. It's going to want to shift in a way that makes less collisions. And how does one make less collisions? Well, with less moles. If there's less particles, there'll be less things to collide. So by increasing the pressure and increasing the amount of collisions, it's going to want to shift in a way to make less moles. And this is going to be based off of the stoichiometry. It's going to be based off of the coefficients. And it's going to shift towards the side that has less moles if the pressure is increased, and shift towards the side that has more moles if the opposite happens. If the pressure decreases, there's going to be less collisions, and the equilibrium is going to want to make more collisions as a result. And one important note is this only affects gas equilibrium. This making more moles or making less moles thing only applies to gas equilibrium. So let's think about this reaction again. On the reactant side, we have 2 moles of hydrogen reacting with 1 mole of oxygen. So we have 3 total moles of gas on the reactant side. And then on the product side, we have 2 moles of gas. So the product side has less moles than the reactant side. So if the pressure was increased, it'll want to shift towards the side with less moles, which would be the product side. So that'll increase the rate of the forward reaction. And if we were to decrease the pressure of the system, it's going to do the opposite. Since there's 2 moles of gas here and 3 moles of gas here, if the pressure goes down, we want to make more collisions, therefore we need more moles. And the reverse rate is going to increase, and we're going to shift towards the reactants. So now let's shift gears a little bit and talk about how Le Chatelier's principle can affect all kinds of reversible reactions. But specifically, we're going to be talking about solubility equilibrium and Ksp and how solubility can be influenced by Le Chatelier's principle. So I briefly mentioned before that there's a equilibrium constant called Ksp. The SP stands for solubility product. And this is a version of an equilibrium constant that describes how soluble an ionic solid, aka a salt, is. And if we have a generic equation to represent this, this is just representing the dissociation of an ionic compound where you have your cation and your anion with some ratio between them, splitting up to make a cation and an anion in solution with a mole ratio between them that's based off of the ratio of those ions in the compound. And the equilibrium expression is going to look like this, where we have Ksp is equal to the ionic concentrations of A and B, both raised to the power of their coefficients. And this is called a solubility product because the equilibrium constant is just equal to the product of those two concentrations. There's no denominator since the solid doesn't have a concentration, so we omit it from the expression. And the larger the Ksp, the more product favored this is, the more soluble the ionic solid or the salt, because it's just going to want to split up and make the individual ions in solution. And this can give us a lot of information about the solubility of a compound, because if our Ksp was, say, 1.6 times 10 to the negative 5, that means it's very reactant favored. That means that the lead chloride, in this case, the lead 2 chloride, doesn't want to split up into individual ions. It'd rather stay in the solid form. However, we think about lead chloride being an insoluble salt, but that doesn't mean it's not soluble at all. It just means it's very minimally soluble. This doesn't want to happen to any significant extent. But there will be some lead ions and some chloride ions in the solution if you were to add some lead 2 chloride salt to water. And we can calculate what the maximum solubility of those ions are going to be, what their saturated ionic concentrations are going to be. And we could do that by setting up an equilibrium expression or a Ksp expression. And if we imagine that the lead ions are X, we can imagine that chloride is going to be 2X, because for every one lead ion, there's going to be 2 chloride ions. And we could set up an equilibrium expression where our lead concentration is X, our chloride concentration is 2X, and it's also going to be raised to the second power because of the way equilibrium expressions work. And we can simplify X times 2X squared to make 4X cubed, because the square is going to affect both the 2 and the X, and then that's all going to be multiplied by X. And then from here, we can solve for X, which in this case is 0.016. And that's going to be the concentration of lead ions, the equilibrium concentration, aka the saturated ion concentration. And since the chloride is 2 times the concentration of the lead, we can just multiply 0.016 by 2, and our chloride ion concentration in this solution is going to be 0.032 molar. I should add units here. All right. So let's apply this. Say the Ksp for lithium fluoride is 1.84 times 10 to the negative 3. Let's solve for the concentrations of lithium ions and fluoride ions at equilibrium. And then also, we're going to use the Ksp for chromium 3 hydroxide, which is 6.30 times 10 to the negative 31, and calculate the concentrations of chromium ions and hydroxide ions at equilibrium. So for this one, it's pretty easy since lithium and fluoride are going to be 1-to-1 in the solution. So if we call lithium X, we can also call fluoride X. And then we can just say that 1.84 times 10 to the negative 3 is equal to X squared. And then solve for X, which in this case is going to be 0.042 molar. And for this one, the Ksp of 6.30 times 10 to the negative 31 is going to be equal to X, standing for the chromium, and then 3X, representing the hydroxide, raised to the third power. And this is going to end up equaling 27x to the fourth power, because the 3 is going to cube the 3 to make 27, and then also cube the x to make x cubed, and then also times another x will give us x to the fourth power. And then we can solve for x, which in this case is going to be 1.24 times 10 to the negative 8. And then we can multiply that by 3 to get 3.71 times 10 to the negative 8, which will be the hydroxide ion concentration. And once again, these are in units of molar. And one quick math tip here. If you ever have something to the fourth power and you're trying to solve for x, if it was a square, you would just do the square root of both sides. If you need to find the fourth power root, you can just raise both powers or both sides of the equation to the 1/4 power. That does the same thing as taking a fourth power root. Now let's talk about something called the common ion effect. And this is basically just an application of Le Chatelier's principle to a solubility equilibrium. And it's described as being when an ionic solid is added to the same solution that has an ion in common with it, the more soluble solid is going to affect the equilibrium of the less soluble one. And when we're talking about soluble salts, we're talking about substances with a Ksp greater than 1. So let's compare lead 2 chloride's solubility to sodium chloride's solubility. We're looking at 1.6 times 10 to the negative 5, which is very reactant favored, meaning that lead 2 chloride is not very soluble, compared with sodium chloride with a Ksp of 36, which is much more product favored, which implies a much more soluble salt. So based off this information, sodium chloride is significantly more soluble. And if we were to add sodium chloride to a solution of lead 2 chloride that's already at equilibrium, it's going to dramatically increase the concentration of chloride. So we already have an equilibrium between the lead 2 chloride and its ions, which, like we said before, is way more reactant favored. But by adding a bunch of chloride to the solution, since the sodium chloride is very soluble, we're going to be increasing the amount of chloride that is in solution. And based off of Le Chatelier's principle, that's going to shift it back towards the reactant side to make even more lead 2 chloride, which is going to dramatically decrease the amount of lead in solution, like I said, based off of Le Chatelier's principle. So let's do a little math for this. So consider a saturated lead 2 chloride solution. Remember, saturated means maximum concentration, or at equilibrium if we were to put as much solid as we could into a solution and see the maximum amount that would dissolve. We determined earlier that the maximum concentrations for a lead 2 chloride solution at equilibrium would be 0.016 molar for the lead and 0.032 molar for the chloride. And say now we're going to add 0.1 moles of sodium chloride to a total of a 1.0 liter solution of the lead 2 chloride. That's going to increase the chloride concentration to 0.132 molar, since the amount of moles of chloride were increased by 0.1. Now we can figure out what's going to happen to the lead by plugging this new chloride ion concentration back into the solubility equilibrium expression for the lead 2 chloride and solve for a new concentration of lead 2 plus. So we have our Ksp value, 1.6 times 10 to the negative 5, is equal to the lead ion concentration times the new chloride concentration, which is 0.132 molar, squared. And then if I do the math, I can solve for the lead 2 plus ion concentration, which is now 9.4 times 10 to the negative 4 molar. So it went from 0.016 to 0.00094. And this is basically making the lead 2 plus ions 17 times less soluble than they were before. So the addition of the sodium chloride to the solution decreased the solubility of the lead 2 chloride by shifting it back towards the reactants. All right, so let's apply this. So a calcium hydroxide solution is at equilibrium, and our equilibrium constant in this case is 5.5 times 10 to the negative 6. So already not a very soluble substance. What is the concentration of calcium and hydroxide? And then we're going to figure out what the concentration of calcium is after we add 1 mole of sodium hydroxide to a 1.0 liter calcium hydroxide solution. So we can set up our Ksp expression. Our Ksp is going to be equal to x, which represents the calcium, times 2x, which represents the hydroxide, squared. That gives us 4x cubed is equal to 5.5 times 10 to the negative 6. We can solve for x, which in this case is going to be 0.011 molar. So that means our calcium ion concentration is 0.011 molar, and our hydroxide concentration is going to be double that, 0.022 molar. And now we're going to add a more soluble solid. So sodium hydroxide is very, very soluble. And we're adding 1 mole of it to a 1.0 liter solution, which means that we're increasing the hydroxide concentration by 1 molar. So 1 molar plus 0.022 molar is going to be 1.022 molar. This is our new hydroxide ion concentration after the sodium hydroxide was added. And now we can solve for the new calcium ion concentration by plugging it back into the Ksp expression. So 5.5 times 10 to the negative 6 is equal to our calcium ion concentration times 1.022 molar squared. And then we can solve for the calcium ion concentration here is now going to be 5.3 times 10 to the negative 6 molar. So you can see this was a dramatic decrease in the amount of calcium ion concentration. So changing the pH can also have a significant effect on the solubility of a salt, specifically if the anion in the salt is basic. So let's give an example here. Consider the mostly insoluble salt of calcium fluoride, which has a Ksp of 5.3 times 10 to the negative 9. So very, very reactant favored. Based off of this Ksp, we can't expect this forward reaction to happen to any significant extent. However, if we apply some Le Chatelier's principle here, we can increase the solubility of fluoride with a trick. And think about the different factors in Le Chatelier's principle. What would cause more shift to the product side? Well, we can't increase the concentration of calcium fluoride since it doesn't have a concentration. Adding more solid is not going to do anything because you can only fit so many ions in the solution based off of the solubility. We could increase the temperature, but that's not going to have a very large effect on an insoluble salt. So what we can do is remove ions somehow. If we can remove some fluoride ions from solution, we can cause more fluoride ions to be produced as a result. And this can be done by way of an acid-base reaction. And fluoride is a basic anion because if we were to add hydrogen ions, aka acid, to the solution, the hydrogen ions and the fluoride are going to combine to make hydrogen fluoride. Hopefully you remember this from the intro to acid-base stuff that we did back in Unit 4. So by adding hydrogen ions, these are going to combine with these small amounts of fluoride that are in solution. Once again, this didn't produce these ions to a very significant extent because the Ksp was so small. But the few fluoride ions that are there in solution are going to combine with hydrogen ions to make HF. And those fluoride ions that were removed are going to cause more fluoride ions to be produced because the equilibrium is going to be upset. And since we took away from the product side, it's going to shift more towards the product side to replace them. So that's going to influence more of the salt to dissolve as a result. And this wouldn't really work with solutions of calcium chloride, calcium bromide, or calcium iodide, or other salts with these anions, chloride, bromide, or iodide. And this is because hydrochloric acid, hydrobromic acid, and hydroiodic acid are all very strong acids, which means that chloride, bromide, and iodide are all weak conjugate bases. If you recall, a strong acid means that it fully dissociates. So that means that HCl is going to split up into H plus and Cl minus completely, having a very high K value. But we're going to talk more about acid and base equilibria in Unit 8. But being a weak conjugate base just means that you're unlikely to combine with hydrogen ions in solution. You're unlikely to accept that hydrogen ion like the fluoride did to form hydrogen fluoride here. And In general, this means that salts with basic ions become more soluble in solutions with low pH. And low pH means high hydrogen ion concentration. And the basic anions include fluoride, which we already talked about, carbonate, acetate, cyanide, sulfide, and bicarbonate. You don't need to have this memorized, but these are likely the anions that you'll see in examples of this. So that is all I have to talk about today. So I'll see you in Unit 8.